Hello everyone. PACO, Paths and Attributes for Common Objects, is a work from Meta AI. It is a large-scale dataset jointly providing object masks, part masks, and object as well as part level attributes. It is sourced from two popular datasets, Elvis and Ego4D, spanning 75 objects, 456 object parts, 55 attributes, and roughly 81,000 images. The dataset is available at the link below. As shown here, we annotate parts and attributes for each object instance separately. When annotated, an object instance has object mask, part mask, as well as object and part attributes. We also provide three benchmark tasks. Part segmentation, where model needs to segment part mask per object instance. Second, instance level attribute detection, where a model needs to produce object attributes and part attributes. Lastly, a task where model needs to recover and localize a specific instance of an object from a dataset based on object, part, and attribute query. PACO is motivated by the need to have richer descriptions for object instances. It enables separating out one instance from another based on fine-grained descriptions like the example shown here. A white bottle with a blue cap from a white bottle with a red cap. Object vocabulary in our dataset contains 75 common objects found in Elvis and Ego4D. The part vocabulary was carefully constructed for each object category by mining from web sources as well as manual curation. Our attribute vocabulary spans colors, patterns, materials, and reflectance. It was chosen based on careful data analysis to have good coverage across all instances in the dataset. Sample object and part masks for a few attribute categories are shown here. Our dataset is also the first to provide both object and part attributes for common objects at such scale. We compare our dataset to contemporary datasets along different axes in more detail in our work. We look at the number of object part categories, the number of object part masks, object masks, attributes per object, attributes per part, and so on. Next, we will go over each of the three associated benchmark tasks supported by the dataset. The first task is similar to object segmentation. However, model is expected to segment each part per object instance with a label and a confidence score. The model should get both object and part label correct for the part mask as shown here. For example, the different object part labels in this image are knife blade, scissor handle, knife handle, scissor blade, and so on. There is one confidence score which combines both the object and the part label. Next, we will look at the evaluation metric for this task. To keep annotation cost bounded, we extended the idea of federated datasets introduced in Elvis to PACO. In particular, for each object part, we provide three sets of images. Negative images that do not contain the object part. Exhaustive positive images where every instance of the object part is annotated. And non-exhaustive images with some missing annotations for the object part. Providing such clear distinct sets of images makes it easy to define a proper and fair metric for evaluation. In particular, we can extend the popular average precision metric used for object segmentation to this new part segmentation task as well. Additionally, we provide baseline models by extending mask RCNN from object segmentation to object path segmentation. We benchmark this model with four different backbones. Here, we show the average precision for both object and object part segmentation. The models are also released on our website. The next task requires a model to both segment the object or object part and also provide attribute labels per segment, along with one single joint confidence score for the object or part label and attribute label. So there would be one label like white plate or metallic plate for objects, and that label would be associated with one score. Similarly, for object part attributes, we would have labels like red bottle cap, plastic bottle body, and so on, and each of those labels would have one associated confidence score. We again adapt the federated setup we visited earlier for this task as well. This allows us to define average precision metric for this task. Here, we consider each object attribute pair like red car and each object part attribute triplet like red car roof or red bottle cap separately. Average precision is computed for for each object attribute pair and each object part attribute triplet separately. We finally average the scores across all object attributes and across all object part attributes to define average precision for object attributes and object part attributes. We also provide baseline mask RCNN models extended to this new task and provide benchmark results for object attributes as well as object part attributes across 4 different baseline models. Finally, we have a task that binds all labels that we introduce together in the form of query-based instance retrieval. Here, a model takes in a fine-grained query like black dog with white ear as input and retrieves a single image containing that specific instance from among 100 other images. The model needs to also localize that instance with a bounding box in the positive image containing the instance. We have queries spanning 3 levels of complexity. Level 1 queries have only one attribute. Example, a blender with white base where the attribute is white. For this query, we have a positive image along with the bounding box for that specific instance, along with a bunch of distractor images shown in red here. The distractor images do not contain any instance corresponding to the query. Similarly, we have level 2 complexity queries with 2 attributes, a metal mug with black handle, and level 3 queries with 3 attributes, a dog with black ear, white foot, and brown leg. We use average recall metric defined in PACO for this task. We compute AR on the top 1 image as well as the top 5 images returned by the model. We provide baseline results by ranking boxes for a query using object and part level attribute scores for each box. We provide more detailed analysis of the baselines in our paper. Thank you for sitting through our presentation. Please do visit our website for data, code, and more.